In this question, we have a plank of mass m1 with a bar of mass m2 placed on it. So we have a plank of mass m1 and on it we have a bar of mass m2. Now it lies on a smooth horizontal plane. So the horizontal surface is smooth. Now a horizontal force growing with time T as F equal to Kt is applied to the bar. So on this particular bar, a force F equal to Kt is applied, which increases with time. Now we need to find how the acceleration of the plank A1 and that of the bar A2 depends on it. If the coefficient of friction between plank and the bar is mu, so the coefficient of friction is mu between plank and the bar. We also need to draw the approximate plots of these dependence. So first of all, when external force is not sufficiently large, these two, that is plank and bar, will move together. So as T is small, frictional force has not crossed the limiting value. Frictional limiting friction, so frictional force is less than equal to limiting friction, that is frictional force is less than equal to mu m to g. Till that moment the plank and the bar will move together. So as they move together, let their acceleration be a. So in this particular situation, for m2 we have a force kt, acceleration a, frictional force to be acting backward, and we have block of mass m1 on which friction is acting forward and its acceleration is also a. So here from we can write kt minus f is equal to m2a and f is equal to m1a. So here from we can write kt is equal to m1 plus m2a, or a is equal to kt by m1 plus m2. So as long as friction has not crossed limiting value, the acceleration is kt by m1 plus m2. This is the acceleration of mass m1 as well as the acceleration of mass m2 when time is lesser than the limiting time, when friction crosses the limiting frictional force. Now when the frictional force reached up to limiting friction, in that situation the force on m2, kt forward, mu m2g is backward, and let acceleration is a2. So here from we can write m2 a2 is equal to kt minus mu m2g, or a2 is equal to kt minus mu m2g by m2. This is the acceleration when friction has reached its limiting value. In this particular situation, acceleration of the plank, that is of mass m1, mu m2g is the force on it, frictional force on it, and let acceleration be a1. So here from we can write mu m2g is equal to m1 a1, or acceleration a1 is equal to mu m2g by m1. So these are the acceleration of the bar and the plank after friction has reached its limiting value. But now we need to find when friction has reached its limiting value, that we need to find. So to find that particular time, here from we can write, from this particular equation we can write friction F is equal to m1 into a, that is equal to m1 into a is kT by m1 plus m2. This is the frictional force, and the moment when friction has reached limiting value, that is, let mu m2g is equal to m1k, let the time be t0 by m1 plus m2. So the time when friction has just reached limiting value, that time is mu m2g by m1 plus m2 by m1k. So here from we can conclude that the plank and the bar has same acceleration before this time, and after this time their accelerations are different. Now if we look at the equations, initially acceleration was a function of time, a linear function of time, so the graph will be a straight line passing through origin before t0. So if we plot the graph between acceleration versus time, then before t0 it is a straight line passing through origin. After the time t0, acceleration a1 is constant. So after time t0, acceleration of the plank is constant a1, and after the time t0, acceleration of a2 is again a straight line with some constant, and it is linear function of time. So this will be a2. So the acceleration versus time plot of the given process is somehow like this.